Hello everyone, my name is Naina and I'm from the Buddhi Academy. So today we'll continue with the chapter, and in today's part we will see about the electronic configuration of the element. In last class we have seen the nomenclatures, right? So in our last video we have seen the periodic table. Okay. What is the general periodic classification? In that we have seen triads, law of octaves, law of triads, then Mendeleev's periodic table, modern periodic table we have seen, right? And also nomenclature. Now, in today's video we will see about the electronic configuration. Now, electronic configuration of elements and the periodic table. Now, in the preceding unit we have learned that an electron in an atom is characterized by a set of 4 quantum numbers, right? Principal quantum number, azimuthal quantum number, spin quantum number, magnetic quantum number. So like that we have 4 quantum numbers. On basis of those 4 quantum numbers the atoms were characterized. In that the main was the principal quantum number, okay, which defines the energy of the shell, okay, which defines the energy level, which is known as shells. Now, we have also studied about the filling of electrons, how electrons were filled. They are filled by Aufbau's law, following the Aufbau's law, right? Now, also referred to as orbitals, that is s, p and d orbitals in an atom. Now, the distribution of electrons into orbitals of an atom is called electronic configuration. So, when you distribute the electrons, okay, into these orbitals, they are known as electronic configuration. Now, an element location in the periodic table reflects the quantum numbers of the last orbital filled. Okay. Now, the location of the element in the periodic table, okay, it is basically arranged on the basis of the last quantum number which is filled in the orbital. Now, in this session we will observe direct connection between the electronic configuration of the element and the long form of periodic table. So in this part we learn the connection between the periodic table and the electronic configuration. So first is the electronic configuration in periods. How the electronic configuration depends or affiliates the periods. Now, the period indicates the value of n for the outermost or valence shell. Now, periods are basically because of the valence shell or the outermost orbit. Now, in other words, successive period in the periodic table is associated with filling of the next higher principal energy level. So, what periods are of? They are of successive thing. Means in one period only one orbital is filled. In the second period addition of second orbital takes place. In third period addition of third orbital takes place. So it is a successive period in the periodic table which is associated with the filling of next higher level, a higher principal energy level, that is n is equal to 1, 2, 3, etc. Now it can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. Now you can easily see that the number of elements, okay, in each period is twice the number of atomic orbitals. Now for example, s, p, d and f. Now each of them have orbitals 1, 3, 5 and 7 respectively, okay. So these are the orbitals of each of the shells. Each shell has this many numbers of orbitals in them. For example, S shell has 1 orbital associated with it. P shell has 3 orbitals associated with it. Similarly, D and F has 5 and 7 orbitals associated with it. But when you fill the orbitals with electron, it is always observed that the number of electrons filled is twice the number of the orbital. Now if D has 5 orbitals, the number of electrons filled in this D orbital is 10, which is twice the number of D orbitals, okay. So similarly with other orbitals also. Now the first period, that is n is equal to 1, starts with the filling of the lowest level 1s, and therefore has two elements, hydrogen and helium. Okay, so the first period, it starts with the filling of 1s orbitals, and it has two atoms associated to it, hydrogen and helium. Hydrogen is 1s1, helium is 1s2. Now here s orbital of the first period is completely filled, and this completes the first shell, that is the K shell. This completes the first K shell. Now next will come your second period. Now what will happen in second period? Second period, along with this 1s, you will be adding 2s and 2p. Along with 1s you will be adding 2s and 2p orbitals. Now lithium, and now it starts with lithium. Second shell, it starts with lithium. Third electron enters the 2s orbital. Lithium, the atomic number is 3, right? So it will be 1s2, and the third atom will enter in 2s, that is 2s1. The next element is beryllium. Beryllium has 4 electrons in it, and it will fill the 1s and 2s orbitals. So both 1s and 2s are completely filled. After 2s is completely filled, the next orbit is added, that is the 2p orbitals, which are filled with electrons. And once your 2p is filled, once your electronic configuration turns 1s2, 2s2 and 2p6, 2p6, 6 means p has 3 orbitals. 3 multiplied by 2, you get 6 electrons filled in 3p orbitals. So 1s2, 2s2, 2p6. This completes the L shell. Now thus there are 8 elements in the second period. Now first period has 2 elements. Second period has 8 elements. So first period 2 elements, second period 8 elements. Let's move to the third period. The third period starts with n is equal to 3. Here 3s orbitals will start getting filling up. Now we have finished 1s, we have finished 2s and 2p. Now next is our third period. In third period it will be 3s, 3p, 3d. These are the 3 shells of the third period. Now it begins with sodium. So the third period starts with sodium, and the electrons start entering into the 3s orbitals. Now successive filling of 3s, 3p orbitals gives rise to the third period of 8 elements, that is from sodium to argon. Once your 3s and 3p are filled, 3s and 3p are completely filled, this gives rise to the third period of 8 elements. Now again third period has 8 elements. Now the fourth period, next is a fourth period. The fourth period, it starts from potassium. Fourth period starts from potassium. The added electrons fills up the 4s orbital. So here 4s orbitals are being filled up. Now once 4s orbitals are filled, now you may note that before 4p orbital is filled, filling up of 3d orbitals become energetically favorable, and we come across the so-called 3d transition series of elements. Now in fourth period there is a twist that we can see. Here in third period I have told you we have 3s, 3p and 3d, but we have also observed that 3d was not being filled in third period, but this 3d is filled in fourth period. Once your 4s orbital is completely filled, the next electron should move into 4p, right? But in this case, it is observed that once 4s orbital is completely filled, the electrons start adding up into 3d orbital, because energetically 4s is, after 4s 3d is the orbital which is present. Okay, and that part where 3d starts filling up, okay, after 4s when 3d starts filling up, that elements we call them as 3d transition series. Okay, now this starts from scandium. Now the 3d transition series, it starts from scandium, okay, which has an electronic configuration of 3d1 4s2. Now the 3d orbitals are filled at zinc. Okay, at zinc the 3d orbitals are completely filled, that is 3d10 4s2. This configuration will attain at 3d at zinc. Now with electronic configuration 3d10 4s2. Okay, now the fourth period ends at krypton. Okay, now the fourth period, it ends at krypton, where 4s2 3d10 4p6, this electronic configuration is attained at krypton, where your fourth period ends, and fourth period has 18 elements altogether. Okay, altogether fourth period we have 18 elements in fourth period. Okay, now next comes our fifth period. Now beginning with the rubidium, it begins with the rubidium. Okay, is similar to the fourth period and contains a 4d transition series. Now fifth period is also similar to the fourth period. Okay, why similar to fourth period? In fourth period what happens, there is 3d molecules or 3d shells which are filling up, right? Now in fifth period also we have a 4d series. Okay, in fourth period we have 3d transition series, and in fifth period we have 4d transition series starting with yttrium. Okay, now this period ends at xenon. Now fifth period, it ends at xenon by the filling up of 5p orbitals, completely filling up of 5p orbitals. The fifth series completes, and the sixth period NS6 contains 32 elements. Okay, now again sixth period, it contains 32 elements, and successive electrons enter 6s, 4f, 5d and 6p orbitals in order, filling up of the 4f orbitals being with cerium and ends at lutetium to give you HF inner transition series. So sixth period, apart from the transition series, we have something called as inner transition series, where F block are involved or F orbital is involved, which is called the lanthanide series. Okay, sixth period also has a lanthanide series, and sixth period has altogether of 32 elements in it. Okay, now fifth period also has 18 elements. Sixth period will have 32 elements. Okay, now similarly we have the last period, that is the seventh period. Similar to sixth period, seventh period also has a filling up of 7s, 5f and 6d and 7p orbitals. Here also 5f is there. Similarly 4f, now we have 5f. Here this 5f is known as 5f inner transition series or actinoid series. So we have lanthanide series and actinoid series. 4f is lanthanide series, 5f is actinoid series. Now the 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure, to preserve the principle of classification by keeping elements with similar properties in a single column. Now 4f and 5f inner transition series, those elements, okay, the elements which start filling up 4f and 5f orbitals, they are placed separately in the periodic table, and it is placed separately to maintain the structure. What type of structure? The electronic or the periodic table. In that periodic table, elements are placed in such a way that their properties are similar, not by their atomic weight but by their properties. So this 4f and 5f inner transition series, the elements in this series have similar properties which doesn't follow with the properties of the transition series. So they are kept separately under the table to follow the principle. Here you can see. So this is the lanthanide and actinide series which are kept separate. Okay. Now next is the group wise electronic configuration. Till now we have seen the electronic configuration with respect to their filling of electrons. Now next we will see group wise electronic configuration, and that is basically in the periods. Okay, this is groups. The elements in same vertical column or group have similar valence shell electrons configuration, the same number of electrons in the outer orbital and similar properties. Now till now what we have seen it in the periods. Now we will see it in the groups. Okay, now groups, they have similar valence shell. Similar valence shell means if I take any one of the group, okay, the shell, the last shell in that group will be same. Okay, either it will be 3D, 4D, 4P. Okay, either it will be 4P, 3D, 4D. The last shell will be same for the groups. And another thing will be this, they will have same number of electrons in that last shell. Okay, for example, the last, that is helium, neon, krypton, argon, xenon, krypton. Okay, all these are the last end molecules. All these molecules have a p orbital in the end. They all have a p orbital in the L, except helium. Okay, except helium, others have p orbital at the end and they have 6 electrons filled in the p orbital. So the last orbital is also same, the number of electrons filled is also same. Okay, and they have similar properties. These are known as noble gases. Okay, so they have similar properties. Now for example, the group 1 elements, that is alkali metals, all have ns1 valence shell electronic configuration as shown below. Now the first group where hydrogen is placed, all those, that lithium, sodium, potassium, rubidium, cesium, fermium, all these molecules, they have at the end S1. The number may be different, it will be 2, 3, 4, 5, 6, 7, the number may be different, but in general it is NS1. S1 is the common thing everywhere that you can see, right? So they have a valence shell is also same, they have S shell in all the molecules, and the number of electron is also same, that is 1 electron in each of the S shell. Now, thus it can be seen that the properties of the element have periodic dependence upon its atomic number and not on relative atomic mass. So this proves that basically from where we have writing this, we are writing it from the atomic number. On the basis of their atomic number we are distributing the electrons, not on the basis of their atomic masses. So here it clearly states that periodic dependence, okay, it is upon the atomic number and not on the relative atomic mass or the atomic mass. Now next is the electronic configuration and types of elements. Okay, that is S, P, D and F block elements. Now the above principle and the electronic configuration of atoms provide the theoretical foundation for the periodic classification. Aufbau's principle is basically given to make it easier for us to write the orbitals, how the electrons are filled. Okay, what is the pattern in which the electrons are filled in the orbital. It makes it more convenient to observe the filling of electron. Now because of Aufbau's principle, there is a theoretical foundation for the periodic classification. Now the elements in a vertical column of the periodic table constitutes a group or a family and exhibit similar chemical behavior. So the elements in the vertical column means like this. Okay, in the vertical column they exhibit similar chemical behavior, so their chemical behavior is same. This similarity arises because these elements have same number and same distribution of electrons in their outermost orbital. Now, why they have a similar chemical behavior? This similar chemical behavior is basically because of the outermost orbital, the electrons present in the outermost orbitals. As I showed you here, all these molecules, they have a similar outermost orbital, that is s orbitals, right? The energy level may be different, but main point to be noted is that they have similar orbitals, and this similar orbital has same number of electrons present in them. Okay, so the outermost orbital is same with same number of electrons filled in them, even though the energy level may differ, but the point remains same, that is they have same number and same distribution of electrons in their outermost orbitals. Okay, now we can classify the elements into 4 blocks. Okay, now how you will classify the elements? We can classify them into 4 blocks: S block, P block, D block and F block. Now, depending on the type of atomic orbitals, they are being filled with electrons. Now, these are classified on the basis of the last shell which is present on the element, okay, or the filling up of the electrons in that particular element orbital. Now, this is illustrated in figure 3.3. Now, let's go for figure 3.3. See here. So, this is the S block, this is the D block, P block and F block. Now, S block is basically because all the s orbitals are being filled in this elements. P block starts getting filled up in this elements. D block starts from scandium. Okay, and F block, this is 4f and 5f orbitals which are start being filling up in this elements. So basically it is put in such a way that the orbital, okay, that starts getting filled up and completely fills. Okay, lithium 2s orbital starts filling up with lithium. Lithium will be 2s1. By the time beryllium comes, it will be 2s2 and the s orbital is completed here only. Now from here, the p orbital starts filling up. So p, 2p1, 2p2, 2p3, 2p4, 2p5 and 2p6. 2p orbitals are completely filled. Got it? So that's why this is the p block elements, because from here 2p orbital starts getting filling up. 2p1, 2, 3, 4, 5 and this will become 6. So 2p orbitals are completely filled. As you know, p orbitals, what they will do, they will be completely filled when there is 6 electrons in the p orbitals, 10 electrons in the d orbitals, 14 electrons in the f orbitals and 2 electrons in the s orbitals. Okay, so once they start getting filled up and they completely fill, that part is that particular block. Okay. We notice 2 expectations to this categorization. Okay, there are 2 expectations from this categorization. Now, strictly helium belongs to the S block, but its position is in the P block along with other group. Okay, 18 element is justified because it has a completely filled valence shell, that is 1s2, and as a result exhibit properties characteristics of other noble gases. Now, since I told you all ki p block means there should be filling up of p orbital, right? But when we look at this, there is a helium here. Okay, but helium only has 1s 2 electrons. It only has s orbitals. Then why it is placed in the category of p block? That is basically because of its characterization or the properties. Being completely filled, okay, 1s orbital, it is completely filled. Helium is completely filled. It exhibits property of the noble gases. Okay, noble gases means the other elements present there, that is neon, argon, krypton, xenon, all those are called as noble gases because of its completely filled valence shell. Okay, now here also helium has a completely filled valence shell, and as a result it exhibits a property similar to noble gases. That's why it is placed in the p block elements. Now the other exception is hydrogen. Okay, it only has one s electron and hence can be placed in group 1 alkali metals. Okay, another one is hydrogen. Hydrogen only has 1s1. Okay, so it is placed in the alkali metals. It can also gain an electron to achieve the noble gas arrangement, and hence it can behave similar to group 17, that is halogen family elements. Because it is a special case, we shall place hydrogen separately at top of the periodic table. Now why hydrogen is placed in between? Hydrogen is placed here, you can see that. Now it is placed here because hydrogen, it has only 1s1 electrons, so it is an alkali metal. But hydrogen has a tendency to take one more electron. Okay, it can take one more electron and become 1s2. By becoming 1s2, hydrogen can attain a completely filled shell, and once it is 1s2, that is completely filled shell, it can also act as an halogen. Okay, or it can act as a noble gas. So because it shows dual behavior, okay, it can behave similar to group 17. It can also get converted to noble gas. Because of this, it has a special case, right? It has two things. One is noble gas. Another thing is it can behave as the group 17, that is the halogen family. So because of these two reasons, hydrogen is placed separately on top of the periodic table. Okay. Now, we will briefly discuss the salient features of the 4 types of elements marked in the periodic table. Now we will discuss all the 4 types of blocks. Okay, now the first one is the S block. Okay, now first one is the S block elements. Now the elements of group 1, that is alkali metals, and group 2, that is alkaline earth metals, which have ns1 and ns2 outermost electronic configurations, belong to the S block elements. Now S block elements, okay, it has 2 columns, right? One is alkali metals and one is alkaline earth metals. So this is alkali metals and this is alkaline earth metal. One with 1s, one with ns1 and another one with ns2. So the one with ns2 is alkaline earth metal, ns1 is the alkali metals. Okay, now they all are reactive metals with low ionization enthalpies. Now what is ionization enthalpy is there in this chapter, but here to understand I will explain it to you in brief, and then once we do that part I will explain you in detail. Ionization enthalpy is basically the energy that is required to remove one electron from that orbit. Okay, so s orbitals, they have low ionization enthalpy. That means they require very less energy to remove an electron. Then they lose the outermost electron readily to form 1+1 ions in case of alkali metals, or +2 ions in case of alkaline earth metal. So since their ionization enthalpy is low, that is the energy required to the electron is low, they lose their electrons readily. That means if you add something, they will give out their electrons. Once they give out their electrons, they will become +1 or +2 ions. Okay. Now the metallic character and the reactivity increases as we go down the group. So as we go down the group, okay, as we go down, their metallic character increases and the reactivity also increases as we go down the group. Now, because of high reactivity, they are never found pure in nature. So since they are highly reactive, okay, you cannot find them in a pure form. Now the compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. Okay, the compounds which are formed in S block except lithium and beryllium, the others are predominantly ionic. They are ionic in nature. Next is a p block elements. Now p block elements comprises those belonging from group 13 to group 18. So p block, it has from group 13 to group 18. All the elements in group 13 to group 18 comes under p block elements. These together with the s block elements are called representative elements or main group elements. So p block elements along with s block elements, they together are known as representative elements or main group elements. Okay, now the outermost electronic configuration of p block elements, it will start from ns2 np1 to ns2 np6. Okay, once it attains ns2 np6, the orbital is completely filled. Okay, now at the end of each period is a noble gas element with a closed valence shell of ns2 np6 configuration. So in the p block elements, okay, in the p block elements, the last block, that is the 18th group, okay, the last row or the 18th group is made of noble gases. Okay, it is made up of noble gases with an electronic configuration of ns2 np6, that is a closed electronic configuration of ns2 np6. Now all the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition or removal of electrons. So the noble gases, okay, the valence shell of these noble gases are completely filled with electron. Being completely filled with electron makes it difficult to alter, because it is completely filled, that means it is stable in its nature. So once it is stable, you can't make any changes to them. Okay, either by addition or removal of electrons, it is very difficult to make alterations in them. Now these noble gases thus exhibit a very low chemical reactivity. So because of their completely filled electronic configuration, and since they are highly stable, it makes it very low in chemical reactivity. Okay, the chemical reactivity is less, okay, compared to the s block elements. Now preceding the noble gas family are two chemically important groups of non-metals. Okay, now before the noble gases, okay, group 17 and group 16. So this is group 17 and this is group 16. Okay, these are preceding groups. Now, these are the most important non-metal groups. Okay, most important groups of non-metals. They are halogens and chalcogens. Okay, so group 17, this is halogen, and group 16, this is chalcogen. So these are the two important non-metallic groups. Now, these two groups of element have highly negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. Why these are important is because both of the electrons or both of the group, halogens as well as chalcogens, they require 1 or 2 electrons to attain a completely filled orbital and to make themselves stable. Okay, so they only require 1 or 2 electrons to make themselves stable. In that case, what they will do is they will take that 1 or 2 electrons from other elements. Okay, because of this, they are known as highly negative electron gain, or they have highly negative electron gain enthalpy. Electron gain enthalpy they have. They can readily accept an electron, because the moment they accept an electron, they will become completely filled. Okay, they will attain a noble gas configuration. So because of that, these two are highly important, because they only require 1 or 2 electrons to complete their valence shells. Okay, now the non-metallic characteristic increases as we move from the left to right across the period, and metallic character increases as we go down the group. So non-metallic character, okay, it increases as we go from left to right of the period, and as we go from top to bottom, the metallic character increases. Okay, so metallic character, it increases from top to bottom, and it increases from left to right. Okay, left to right, top to bottom, it increases. Now next is the D block elements or the transition metals. Now these are the elements of group 3 to 12. Okay, group 3 to 12 in the center of the periodic table. Now these are characterized by filling of inner d orbitals by electrons and are therefore referred to as D block elements. Okay, now these are the elements of group 13 to 12 in the center of the periodic table. Now these are characterized by the filling of inner d orbitals. Inner d orbitals means it is between 4s and 4p orbitals. So that's why it is known as inner d orbitals. Now these elements have the general outer electronic configuration of n-1, d 1 to 10 and ns0 to 2. Now why n-1? Because it is in the fourth period, so n will be 4, but what is the orbital is 3d orbitals, that's why it is n-1. Except for palladium, where its electronic configuration is 4d10 5s0. There is an exception for palladium where the electronic configuration is 4d10 and 5s0. Now they are all metals. Okay, the D block elements, they are all metals. They mostly form colored ions. Okay, they are metal, they form colored ions, exhibit variable valencies, that is oxidation state. They can have different valencies. They show paramagnetism and oftenly used as catalyst. Okay, these are the properties of D block elements. Now however, zinc, cadmium and mercury, okay, there is an exception for all these three elements, zinc, cadmium and mercury, which has an electronic configuration of D10S2. Okay, a completely filled electronic configuration. They do not show most of the properties of the transition elements. Because of their completely filled electronic configuration, these three molecules, they doesn't exhibit much of the properties, or they doesn't show the properties similar to transition elements. In a way, transition metals form a bridge between the chemically active metals of S block elements and the less active metals of elements of group 13 and 14, and thus take their familiar name transition elements. Now why D block is named as transition elements is because it is in between S and P block elements. Okay, so the properties of transition elements is quite similar to S and P block elements. So it is a bridge. Okay, it is a connecting bridge between S block and P block elements. S block being highly reactive and P block being low in reactivity, they combine together with the help of the D block elements, and since it is in between and shows a shifting towards both the periods, both the blocks, that is S and P block, it has the name that is transition elements. Now next one is a F block elements or the inner transition elements. Now the two rows of elements at the bottom of the periods are called lanthanoids and actinoids. Okay, now at the end I showed you all two blocks, right? Two boxes I had showed you all. These are lanthanides and actinides. These are inner transition or F block elements. Now they are characterized by the outer electronic configuration of n-2f, n-1d and ns2. So it is F, D and S. Okay. Now the last electron added to each element is filled in F orbital. So here the last electron that is added, it fills in the F orbitals. Now these two series of elements are hence called the inner transition elements. So these are known as inner transition elements, F block elements or F block elements. Now they are all metals. Again, similar to transition metals, these are also metals. Within each series, the properties of the element are quite similar. So each series has similar properties. Now the chemistry of the early actinoids is more complicated than the corresponding lanthanoids. So when you compare both the series, that is lanthanoid and actinoid series are more complicated than lanthanoids. Now this is because of the large number of oxidation states that is possible for actinoid elements. Now why there is a complication in actinoids than lanthanoids? This is basically because of their valencies. Okay, they show huge number of valencies or oxidation states. Okay, now actinoid elements are radioactive. So actinoid elements, being a metal, they are also radioactive in nature. Okay, they are radioactive metals. Now many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. So many of the actinoid elements, okay, many of the elements present in the actinoid series, they are either produced in nanograms, that is in very less quantity, or they are the product of nuclear reactions, and their chemistry is not fully studied. So the elements after uranium are called transuranium elements. So the elements after uranium, okay, after uranium, whatever elements are there, they are called as transuranium elements. Now next is metals, non-metals and metalloids. Okay, now in addition to displaying the classification of elements into S, P, D and F blocks, there is a classification of elements based on their properties. Now the elements can be divided into metals and non-metals. Now metals comprise more than 78% of the all known elements and appear on the left side of the periodic table. So on the left side of the periodic table appears the metals. Okay, on the left side it appears the metals, and it comprises almost 78% of the all known elements that appears in the periodic table. Now, metals are usually solids at room temperature. Okay, mercury is an exception. Okay, mercury shows an exception. So metals, they are usually solid at room temperature. Gallium and cesium have a very low melting point. So exceptions are mercury, gallium and cesium, which shows a very low melting points. Okay, that is 303K to 302K respectively. So metals, they usually have a high melting and boiling points. Okay, now they are good conductors of heat and electricity. So metals properties, I think you all have been studying it from your 8th standard or something. So metals, they have high melting and boiling points. They are good conductors of heat and electricity. I hope everyone knows this point. Now they are malleable. Now what is malleability? Malleability means you can convert a metal into thin sheets, okay, by hammering it. Hammering means by beating it, you can convert it into thin flattened sheets. For example, aluminium foils you have, right? So you can convert it into a sheet forms. Okay, so that is malleable. Again, they are ductile. Ductile means you can convert them into wires. Copper wires, we use them for conduction of electricity, right? So they can be converted into wires also. Now in contrast, non-metals are located at the top right hand side of the periodic table. So where are non-metals present? If metals are present on the left hand side, obviously non-metals are present on the right hand side. Now in fact, in a horizontal row, the property of elements change from metallic on the left to non-metallic on the right. So if we go horizontally, okay, the metallic characteristic, okay, it will change from metallic to non-metallic as we go from left to right. Okay, as we go from left to right, the metallic characteristic changes from metallic to non-metallic. Okay, now non-metals are usually solids or gases at room temperature. Metals, They are solid at room temperature, whereas non-metals, they can be either solids or gases at room temperature with a low melting and boiling points. So their melting and boiling point is also low. Boron and carbon are exceptions. So here again there is an exception for boron and carbon. Now they are poor conductors of heat and electricity. Again, you know, non-metals, they are poor conductors of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. So most of the non-metals, they are soft or mushy kind of, so they are not malleable or ductile. Now the elements become more metallic as we go down the group. Okay, so their metallic character increases as we go down the group. Okay. Now the non-metallic character increases as one goes from left to right across the periodic table. As I already told you, when you go from left to right, the non-metallic characteristic increases. Now the change from metallic to non-metallic character is not abrupt as shown by the thick zigzag line. So it is not abrupt. Abrupt means it is not directly changing from metals to non-metals. Okay. Now the elements like silicon, germanium, arsenic, antimony and tellurium, they are the bordering elements. These line and running diagonally across the periodic table show property that are characteristic of both metals and metalloids. So let's see these elements, that is silicon, germanium, arsenic. Okay, so silicon, germanium, arsenic, tellurium. Okay, so these are the molecules. Okay, silicon, germanium, arsenic, tellurium, antimony. Okay, so these are the elements which show both properties of metals as well as properties of non-metals. They become the border line. Okay, they are the border line for the separation of metallic and non-metallic molecules, and those elements, they follow or they have both metallic as well as non-metallic characteristics. Okay, both metals and non-metal, properties of both metals and non-metals. And these elements which have similar property for metals and non-metals existing in themselves, they are called as semi-metals or metalloids. Okay, now I hope you all know what are metals, non-metals and metalloids. So in today's video we have seen about the electronic configuration, how it is associated with periods as well as in group, how electronic configuration is associated. Then we have seen different blocks of the periodic table, that is S block, P block, D block and F blocks. We have also seen metals, non-metals and metalloids. So thank you for watching my video. Please do like, share and subscribe to our channel.